I guess I'm going to call this session a practice. And what I'll do is share Blackboard, which should be right here. I'm already in the course. So there's the course, and I put this practice in lessons and reviews under Exam 3, Chemical Composition. And let's see, where did I put it? There she is. So I was just telling Brett, we're really ahead of the game. I don't know how I got this schedule so off that we have an extra day in there that's really nothing to do. So I said, well, we might as well make our time constructive. So I put together this little practice test. It's really not a test. The Blackboard format was the only way I could think of quickly to get it in a shareable form. So let's see, where did I put it? I think I put it under practice test. So we're in lessons and reviews, Exam 3. In case you want to go find it later, you can play around with it. And then practice tests. So there are several practice tests in here that you can drill with, but I created this one right here, especially for today, but it'll be open continuously. And then we'll just treat it like a test. So there, that ought to look familiar. And then continue. And we have these several problems that we're going to work through. Let me see, I got too much stuff covering up my screen, so I'm going to reposition things. Okay. Now, I'm not sure, that might be hard to see unless I can increase. Maybe I can change the view. Yep. Used to work. Not anymore. Okay, so can everybody see the problems well enough so that we can get to work on them?
Yes.
Okay. So you're going to need a piece of paper and a pencil at least to work these out. I need to do the same. So I'll just get my notepad out and find a blank page. And what I'll do is we'll just take them one at a time. And what you'll do is take the problem and work it out yourself. And I'll work it out here in my own time. And then I'll double that time. So I need to get my stopwatch out. I'll double that time and see if you guys can get it. Maybe even triple. It just depends on the difficulty of the problem. Let's see. Where's my, here it is. So I need a stopwatch. There you go. Okay. So if you're ready, we'll do question number 1. And start now. How many atoms are present in 86.9 grams of PT? What's PT? You got to think of that. You might need your periodic table too, right? So does everybody have a periodic table handy, or do we need to stop and wait for you to get it? Because I'm sure you're going to need it more than once. I'll stop. Let me stop that and be sure everybody's got a periodic table. Okay, everybody ready?
Yeah, I got one.
Okay. Brett, you got one too? Uh-oh. Did I scare him off? He could have lost his connection. I don't know. The weather's not looking too good out there.
Yeah.
Okay, we'll continue on. All right, I'll start my timer again. And there we go. So question number 1. 6.9 grams. There he is. You have your periodic table, Brett? So you can do question 1.
I do not, sir.
All right, you need to find a copy somewhere. Look in your, if you don't have access to the documents that I've made available, then look in your textbook. Do you have a textbook handy?
Yes.
Okay. Textbook. Let's see. Yeah. Inside the front cover. That should be sufficient. It'll have atomic weights. So I'm giving you a hint. You're going to need atomic weight to, actually you're going to need more than that. You're going to need atomic weight and you're going to need Avogadro's number to do this one. So 86.9 grams of platinum. This is a dimensional analysis, conversion factor problem. I'll give you a hint. So let's see, looking, can I see that far? Oh, I need to get a little closer with my eyes. So I'll pull out my, so you got to find PT. Okay. And then do that. And the question, always look back at the question. Yep, okay, how many atoms? Yep, that'll do it. Okay, so I need my calculator. You're gonna need a calculator too. All right. So let's see. Significant figures. I'll have this much. Okay. I'm done in 3 minutes. So I'll give you guys another 3 to 5 minutes, and then we'll check your answers. See how you did. And it's multiple choice, so we just pick the closest one to the answer we get. Okay, that's 6 minutes. Let's check our answers. Who wants to go first? Natasha, you have an answer?
Is the first one is it first one C?
No, sorry. How about you, Brett?
E.
That's correct. So, just for the benefit of our viewing audience, this is the approach. And you tell me, oh, you must have done it this way, Brett, to get the right answer. So you start off with, what do you know? 86.9 grams of platinum. And you're headed for the number of atoms. You gotta figure how you get there. Well, there's no direct conversion factor to go from grams to atoms, correct? So you got to go by steps. So we're going to go first grams to moles. So that's a counting number. That's a mass. And you need 195.08 to give you moles. Now we can go to atoms with moles and Avogadro's numbers. Like that. And that gives you 2.68 times 10 to the 23rd. Right? And that's E. Okay. Do you see, Natasha, where you went wrong?
Yeah, I see it now.
Okay. It looks to me like you may have only gone one step just with the atomic mass, and you didn't go from moles to atoms with Avogadro's number. That's what I'm guessing.
Yeah, that's kind of what I did.
Yeah. Okay. So let's take a look at number 2 and see if we can figure that one out. All right, I'm going to start my timer now. 1.85 mole sample of H2O2 weighs what? Okay. Okay, I'm done. So let's see. That's a minute and a half. I'll give you a 3 minutes. Let's see what it's called. Yeah. And 3 minutes. Okay. How about you, Natasha? You got an answer for me? Number 2, 1.85 gram mole sample of H2O2, which is hydrogen peroxide. How much would that weigh?
Is the answer C?
No. How about you, Brett?
D.
Say again?
D.
You say B?
D.
A. That's correct. Okay. So this is another conversion factor. Starting off with 1.85 moles of hydrogen peroxide. You need to end up with grams. Now, as it turns out, there is a direct route to that one. Anytime you see grams per mole, you think molar mass. But we've got a compound here, so we can't use anything that's, well, we use information from the periodic table, but we can't, there's no direct value for that. You have to add it up. So for 2 hydrogens, right, and 2 oxygens, we get, let's see, 3402. So it's 34.02 grams per mole. And that's why the answer is 62.9. Okay. Let's see. This one should be fairly simple. Question 3. All right. Start the timer now. What's the molar mass of Li3PO4? Be good to know how to name that too. PO4. Lithium phosphate. All right. Okay, that's just over a minute. We'll call it at 2 minutes.
I think I got the answer for this one.
Okay,
Is it B?
I'm sorry?
Is it B? 115 point.
Yes, matter of fact, it is.
Okay, good.
Is that what you got, Brett?
Yes.
Okay. All right, well, that one's pretty simple. I don't even need to put that on the board. Both of you got it. You just have to be sure, and you got to look up atomic weights for each one of the elements, and you have to multiply by how many there are, then just add them all together. So that was fairly simple. All right, 4 is going to take a little bit more work. This might take a few minutes. If you remember the methodology that I gave you for deriving empirical formula from the percent composition. All right, I'm gonna give you a hint. So the analysis is 12.1% carbon. And 16.2% oxygen. And 71.7% chlorine. Oops. All right. So I hope that rings a bell. I'm gonna start my timer now. Okay, so it didn't take as long as I thought it would. So I'm at 2 minutes. I'll give you till 4 minutes. Okay. So reset that. How about it? What's the answer? Do you need some more time?
Is it maybe E?
No, not E. How about you, Brett?
C.
You said A,
C.
D,
No, C.
C. Okay. No, that's not quite it either. Okay. This one took a little bit more brain power, experience, practice. When we got this percentage composition for each of our elements, and remember, we want the empirical formula, which is just the simplest whole number ratio. It doesn't have to be the exact molecular ratio of elements. So the simplest whole number ratio is derived by converting mass into moles, but we don't have mass yet. But we do have mass percent, which means parts per 100. So if that's 12.1%, we could say, well, it's 12.1 grams per 100 grams of total sample. So if we say, assume 100 grams of sample, then that makes this one 12.1 grams, 16.2 grams, and 71.7 grams. Now we can convert to moles because the empirical formula is a molar ratio. That's ratio of numbers of atoms. So what we have to do is convert this to moles. Grams on the bottom, moles on the top. Right? So carbon is 12.01 grams per mole. Oxygen is 16.
I'm
And
sorry. What's the name of the practice test that we doing? Because my computer had shut down for a second.
what's the name of it?
Yeah.
There it is. It starts off with today's date and says Chapter 8, Chemical Composition Class Practice.
Okay. Thank you.
And there we go. Back to question 4. Oh, I didn't mark that. This is question 4. Okay, so we can convert these to moles, and then the ratio of those moles will establish the empirical formula. So we get 1.007 and 1.013, and then chlorine is 2.006. Okay, this is moles of each. Now, one thing that you're allowed to do with this technique is to round to the nearest whole number. And if you're really, really close to that whole number, then it's even better. So this one's really close to 1, that one's close to 1, and that one's close to 2. So the ratio is 1 to 1 to 2. So that means our formula is one of those, and one of those. Okay, COCl2, which is A. Now we got lucky, right? Or the problem was created to give us these results. But very often, these values here are not close to whole numbers. So then you have to go an extra step to, this is the ratio, right? We've established the ratio moles to moles to moles, but you want to get whole numbers. So then the next trick is to convert these into something that resembles whole numbers. And if they were very far from whole numbers, each one, or just one of them actually, then you would divide the whole thing through each one by the smallest one. So we divide by that one to give us 1, and this one would give us a little over 1, and this will give us a little over 2, a little less than 2 maybe. But we didn't have to do that because they were so close to whole numbers. All right, so let's erase this and take a look at the next one. All right, number 5 it is, I think. Okay, this is a fairly simple one. I'll start the timer now.
Are we supposed to have the same problems?
No.
Okay, just making sure.
Right, you need to focus on the shared screen.
Okay.
The reason for that is, I might have mentioned it before you arrived. Let me stop the timer. These 20 questions for this practice test are randomly chosen by the Blackboard system from a pool that I have of maybe over 100 questions. So they're going to be different every time you go in. If you want to take this test, if you want to go in and do this on your own, then each time you go in, it'll be a different set. Okay, I'll start it back up again. There we go. And let's see.
Sorry, I was just wondering because I was working both of them out. That's why it was taking so long.
Yeah, if you're looking at it on your end, you're going to see a completely different set.
Okay.
Which is not bad. I mean, if you want to drill on these problems, then it's good to have something new, to a different set each time you try it. Let's see, where was I? Here we go. And okay. So that's 1.5 minutes. So we'll go at 3 minutes. So this is number 5. Of course, our remote classmates will be watching this, and they'll see the shared screen, so they'll get the right questions to go by. And you can come back and review it too if you want. that's 3 minutes. I gotta squelch that junk call. Okay, number 5, 4.29 moles of water weighs how much? Anybody? No guesses? Do you need more time?
Yeah, I think
Say again?
I think I almost got it.
Oh, okay.
And he said grams.
In grams,
Is it 77.3 rounded up?
Yep, that's
Okay.
it. Yep, got it. You get that, Brett?
Yes.
Okay. That's good to know. I think that's a fairly simple conversion. You just need to know the molar mass of water. Use that as your conversion factor. So I'm not even going to put it on the board. Yeah, maybe I will, since we do have late viewers. So you have 4.29 moles of water. And we need to convert that to grams. So grams and moles, you need 18.02 is your molar mass for water. It's 2 hydrogens at 1.01 each and 16 for 1 oxygen. And then you get 77.2 grams, right? No, 3. Okay, so that was 5. Let's see what we're dealing with 6. Okay, this one should be fairly simple. I'll start the timer now. The Okay, that's 3/4 of a minute. We'll go 1.5 minutes. All right. What'd you get?
D.
No, sorry. How about you, Brett?
A.
Yep. 0.878. Okay. So what we have to do to convert this to moles, the conversion factor cancels grams and leaves with moles. So we need the molar mass of NO2. That much for nitrogen, and then 2 times 16 for oxygen gives us 46.01, which leaves us with 0.878 moles, I believe. Yeah. Now, is that reasonable? Well, if that's accurate, then the denominator is bigger than the numerator, so the answer has to be less than 1. And it is. So it makes sense. It could be Natasha, you might have got them switched like that and divided 46 by 40. That would have given you 1.14 in that neighborhood. That's my guess.
All right.
Okay. And you know, that can happen even if you set the problem up right and you put the numbers in your calculator wrong. Then, you know, what do they say? Garbage in, garbage out. That's all computers do. If you put the right information in, hit the right buttons, you'll get the right answer. But if you put the information in wrong, computer doesn't know any different. It just does what it does. Okay, let's see. What do we got for 7? Let's see. All right, these are starting to get redundant, aren't they? But maybe practice is good. So let's just take them in stride. Number 7, and I'll start my timer now. "30 seconds. We'll call it at 1 minute and 10 seconds. That's it. Number 7. Okay, let's see what we got. We got 0.94 moles of hydrogen, and based on the answers, we're trying to convert that to mass in grams. So how are we doing?
Is it B?
Let's see. B is no. What'd you get, Brett? I have a feeling you got it right.
D.
B?
D.
D. No. It's actually C. 1.9 grams. The common mistake that's made with this type of conversion is you forget to double your hydrogen. You get 2 of them. And then rounded off to 2 significant figures is 1.9 grams. All right, let's see. How about what's 8 coming up here? Okay, this one might be a little more challenging. I was kind of hoping we'd have a challenging one along the way. So I'll start my timer now. What is the mass of 76 atoms of copper in grams? Right. All right. So I'll stop it at 2 minutes and 10 seconds. You got about another minute. $76 atoms. Get off that hot bed. Get off that hot bed. Go get a drink of water. Go get a drink of water. Okay. All right. What's the answer for number 8? No ideas? Well,
No, I'm lost on this one.
okay. We can eliminate 2 right off the bat. Nobody's going to believe that even that many atoms is going to weigh 63.5 grams. That's ridiculous. And definitely not 4,800 grams. So it's got to be A, C, or D. Well, not even C. Look at that, 10 to the 23rd grams. I mean, that's like an aircraft carrier. So it's got to be A or D. What do you think, Brett?
A.
Yep, that's it. So we got 76. This is a chained conversion. You got to convert atoms into moles because molar mass makes the conversion from moles to grams. And that's not moles yet. Okay, so now we got moles. We can convert to grams, right? So our moles cancel, our atoms cancel. It leaves us with grams here, but we need, what's the molar mass of copper? 63.55. Right? And that gives you the 10 to the minus 21, right? Minus 21 grams. Now you may question, let's see, that was A, wasn't it? Yeah, A. You may question the significant figures of this value. Looks like there are 3 of them there, and there's only 2 here. But remember, this is one of those cases where you're counting. This is a counting number, so it's an exact number. In other words, infinite number of significant figures when you're counting, like counting pencils. So we could have as many here as we want, because conversion factors, they're not limiting either. So we actually have no limiting significant figures in that whole calculation. So we could take this out as many decimals as we want. Okay, that was 8. And let's see, 9. Which of the following is the molecular formula of a compound with empirical formula CH2O and the molar mass of 240? Okay, that's good. So this one, you don't even have to work out the empirical formula. They give it to you. They just want the last step of the process. Find the molar mass. Find the molecular formula. Okay, so that's number 9. And I'll start the timer now and give you a head start. I'll get to it in a second. All right. So, okay. I'll give you another minute and a half. While you're doing that, I'm going to let the dog out on the deck. You need to go outside? Okay, I'm back. Let's see how we're doing on time. That's long enough. All right. What do you think? For number 9, what's the molecular formula for a compound that has empirical formula of CH2O and a molar mass of 240 grams per mole? No ideas? This one might stump you, I admit.
D.
No. Any ideas, Brett?
A.
No. Okay, here we go. So we got number 9 was CH2O. So CH2O is the empirical formula. The molecular formula is going to require some multiplier here. And remember, when you multiply times everything inside, if this has a given molar mass, then that multiplier, not only does it multiply the number of each of the atoms in here, it also multiplies the molar mass. So if you compare the molar masses of the two, then you can deduce X. So what I call that, when you have the empirical formula and you determine the molar mass for the empirical formula, I call it the empirical weight. So the empirical weight for this one would be 12.01 and 2 times 1.01 and 16. Right? So that would be 30.03 grams per mole. But we're given the molar mass for the actual compound, the molecular weight. So the ratio of the two, the molecular weight ratio to the empirical weight, is equal to 240 divided by 30.03. Right? And that's approximately 8. It needs to be approximately the closest whole number, because it doesn't make any sense to multiply this by a fraction. So if we multiply that by 8, then we get C8H16O8. And that would turn out to be B, right? Okay. Keep losing your connection, Brett, huh? Number 10. So this is, let's see. Let's get my bearings here. Okay, number 10. You got 1 mole of each compound below. Which of the following has the greatest molar mass? Now this one's going to require that you know how to write the compound. That's my hint. Got to be able to write the compound formula before you can determine the molar mass. So this is going to take a little extra time. I'll give you a head start. Right. Okay, here we go. Okay. Now we can do some addition. Okay. Now we just crunch some numbers. Okay. Okay, that's 4 minutes. I'll call it at 8.5. Refill my drink while waiting.
Is it A? Let's see, this is number 10. D and E.
Give me another minute. Okay, 4, 3, 2, 1. All right, what's the verdict? Which one of these compounds has the greatest molar mass? No guesses? Did we stump the band this time?
Was it lead? The A?
A?
Yeah.
No. Any ideas, Brett?
C.
Did you say B or D?
C.
Oh, E. Yes. Exactly right. Now for the benefit of our viewing audience. First, we have to write the compounds. So lead 4 oxide. Got lead and oxygen. And since oxygen's always 2- and lead's 4+, that means we need 2 of those. Barium and carbonate is a polyatomic ion. It has a 2- charge, barium has a 2+ charge, because barium is an alkaline earth, always 2+. Ammonium nitrate, that's one where we have 2 polyatomic ions. That's a minus and that's a plus, so you only need 1 of each. Sodium hydroxide. Hydroxide is a polyatomic. It's a -1. Sodium is a +1 because it's an alkali metal. And then iron 3 sulfate. So there's iron with its 3+, and there's sulfate with its 2-. So the way you balance that one is you just cross multiply. Bring the 2 over here and the 3 on the outside of that parenthesis. Now that we have our formulas, we can add up their molar masses. All right, so lead is 207.2, and then we have 2 times 16 for oxygen, and that gives us 239.2 grams per mole. Right. All of these are grams per mole. Barium is a pretty heavy one, not as heavy as lead. And then we have carbon, only 1 of them, but we have 3 oxygens. So that equals 197.34. Okay. Ammonium nitrate. We have 2 nitrogens. Right? And we have 4 hydrogens. And we have 3 oxygens. For a total of 80.06. Then sodium hydroxide is, sodium is 23, oxygen is 16, and hydrogen is 1.01, for a total of 40.01. And then iron, 2 irons, 55, 85. And then how many sulfurs? 3 sulfurs, which is 3207. And then 12 oxygens, 3 times 4. And all that added up is 399.9. So there's your answer. Okay, so everything hinges on being able to write the compound formula. All right, so we're halfway there. Number 11. All right, you have 2 beakers on your lab table. Beaker A contains 3207 grams of sulfur, and beaker B contains 74.92 grams of arsenic. Which beaker contains more numbers of atoms? All right, so I'm going to start the timer now. That was quick. 1 minute, I'll give you 2. Okay. What's the verdict for number 11? Which beaker contains more atoms? No idea? It's kind of a trick question, actually. No, nobody guesses? All right, well, let's look at it. So you got beaker A with 3207 grams of sulfur. And beaker B with 74.92 grams. 492 grams of arsenic. Which ones has the most number of atoms? So you really only need to know counting, right? You don't have to know exactly the number of atoms. We could find out the number of moles, and that would satisfy for the answer, to answer the question, which has the most? Well, when you start to do the conversion, right, go from grams to moles, you notice that the molar mass of arsenic is 32.07 grams per mole. And you look at arsenic, that's sulfur, arsenic, it's 74.92 grams per mole. So what do you got? You got 1 mole here, you got 1 mole here. They're the same. So A has to be the answer. Both beakers are the same because they have the same number of moles, therefore they have the same number of atoms. So that's why I said it's kind of a trick question. Send you off in a wild goose chase trying to calculate the number of atoms when really all you need to do to answer the question is just compare. You know, compare the number of moles of each. How about, this is a good one. How about 12? Okay, start my timer now. Okay, let's see, 5 molecules. Okay, crunch some numbers. Oh, I didn't even read the question right. It's asking for the answer in atomic mass units or in grams. Right? Okay, so five molecules of chlorine. Start that one over again. Wait. Okay, it took me longer than expected. 2 1/4, so I may call it at 5 1/2. Okay. About a minute. And there it is. Okay. Number 12. Figure out the answer. It helps if with a multiple choice test to look at the answers to see what form the answer needs to take. I just jumped on my horse and rode off in every direction before looking at the units of measure for the answers. So anybody got an idea? No? All right. 12. So we've got 5 molecules of chlorine. Molecules of chlorine. All right. Here's the first stumbling block. If you don't remember that chlorine is a diatomic molecule at 1 atmosphere pressure and room temperature, then you're lost. Right. There's your molecule. Now, we want to convert that to atoms. So how many atoms is that? Well, right, 2 atoms per molecule. So we got 10 atoms. Now we want to convert it to something that's in the list of answers. right? Grams, look at the grams, 178 grams for 5 molecules. I don't think so. You know, you're not going to have 5 molecules weigh enough that you can feel them in your hand. So the ones that 178 and 355 grams, they can't be true. That's ridiculous. It's got to be B, D, or E. Atomic mass units. So we're going for atomic mass units. So how many atomic mass units per atom? $35, $45. Right. So now 10 times 35, 45, rounded off, is 355. Atomic mass units. So that's why the answer is B. All right. Let's see what 13 has to offer. Convert 672.8 grams of magnesium chloride equals how many units of magnesium chloride? Notice the way that question is worded. Why did this say units of magnesium chloride and not molecules? Right. The reason is magnesium chloride is not a molecule. Molecules bound tightly together and it behaves as a single unit. Magnesium chloride in solid form is part of a crystal lattice. It's magnesium, chlorine, chlorine, magnesium, chlorine, positives and negatives opposite one another. So the simplest ratio of magnesium to chlorine in that crystal structure is 1 magnesium and 2 chlorines. So that's why it's a formula unit. All right, so now I'll start my timer and we can figure that one out. Okay, that was give you another 2.5 minutes. I'll call it at 5. Mitzi. Squeaky bird. Mitzi, Mitzi, Mitzi. This was 13. Okay, about half a minute.
Supply. Hi, this is James, and I am a client care coordinator over here at GSI. Just reaching out in regards to some material you requested from us, having to do with our free bank failure survival guide. You had concerns regarding the banking financial institutions with laws implemented
Okay.
that allow them to freeze these bank and retirement accounts, putting depositors at risk.
Okay, so number 13. Any ideas? I can see where one possible error might arise. And of course, a good multiple choice test takes into account different errors that test takers might make in the process, and the answer that they get, the wrong answer they get, might be one of the selections. So, what do you think? A, B, C, D, or E?
B.
Did you say B?
Yes.
No. Sorry. B would be too small, right? Fraction of a unit. If you got that many grams of magnesium chloride, it's going to be a substantial number. What do you think, Brett?
A.
No, that's still too small. Okay. I'll show you where I had my question. 672 grams of magnesium chloride. So if you're going to talk about units of that MgCl2, we're talking about numbers of. So we definitely have to convert to moles. So we need a molar mass for magnesium chloride, and I calculated at 95.21. If you do that calculation, then you get 7.066. So that's so many moles, but that's not the number of units. That many grams, units is how many actual numbers of MgCl2s do you have. So you got to go the next step and convert moles to units. And that's Avogadro's number. And that makes it a fairly substantial number. 10 to the 24th. Okay. So if I had stopped here and put E for the answer, I would have been wrong. Because it's not asking for the number of moles, it's asking for the number of individual units. So that's why the answer is C. That was 13. Let's look at 14. Okay. Scroll up a little bit here. The empirical formula for a compound is C2H5O, and its mass is 270 AMUs. Calculates its molecular formula. Okay, this is kind of like the one before, with a twist. So let me start my timer now. And starting information. Empirical formula, C2H5O. O. And the yeah. Okay. Well, no, I didn't get the right number for that one. Let me see what I did wrong. Hmm. You know, I don't think the answer's there. Yeah, that's a faulty question. The answer's not there. So I'm not going to put anybody on the spot for this one. Let's just work it out and find out what the real answer is. So for 14, you've got C2H5O. C2H5O. And this is the molecular weight of the actual molecule. So what would be the weight of this molecule in atomic mass units? Well, you need 2 times that one, right? 2 times 12.01 plus 5 times 1.01 plus 16. Right? Now let's see what the empirical weight would be. Because these values can be either grams per mole, or they can be atomic mass units per atom. And that's what we're doing here, because that's in atomic mass units. We're going to do AMUs down here. All right, so 12.01 for carbon times 2. And then 5 times 1.01, add that, and then 16 for the oxygen. So that's 45.07. All right, so the ratio of the two tells us what X is. So we need to divide this one by this one. 270 is 6, rounded off to the nearest whole number. Right? So if this is 6, then our formula would be C12H30O6. Now let's see if we add these atomic mass units up, do we get 270? So 12 enter and 12.01. So for the carbon is 144.12, and then 30 times the hydrogen. Add that in, and then 6 oxygens. Add that in. We get 270.4, which is close enough. And you'll notice that that answer is nowhere in the selections, right? So that's a bad question. So if it were me and I were remaking the question, I would do one of two things. I'd put the right one in there as a selection, or I'd pick one that was the proper ratio, right? 2, 5, and 1. Right? It has to be multiplied by a whole number. So if any of them are not ratios of 2, 5, and 1, you could throw those out. Take one of those and substitute for it the correct answer, or take one of these that's the proper ratio and calculate its atomic mass units for the molecule and plug that in there. Instead of 270, put in the true number. So that's how I would fix it. But the short version is the question as written is wrong. There's no answer in that group. All right, let's move on to, we're doing good on time. Let's move on to 15. How many moles does 13.3 grams of copper contain? All right. This should be fairly simple. We've done one like that before today. So let's see, 15. And I'll start the timer now. All right, let's see. Headed for moles, which is 63.55. All right. Okay, that was a minute. I'll give you till 2 minutes. All right. This one should be easy. What's the answer? No takers? Okay. Let's work it out. We got grams and we're headed for moles, right? How many moles does that represent? We need to cancel grams and leave us with moles. So the magic number is molar mass. And if your calculator spits it out in scientific notation, notice that some of the answers are in standard notation. So you need to convert just to be sure. And mine spit it out as 2.09 times 10 to the minus 1, which is the same as 0.209. Okay, and that happens to be E. All right. Oh, they're nice with this one. They didn't make you remember that nitrogen is a diatomic gas. So I'll start the timer now. 16. Is that's sort of a trick question, isn't it?
Yeah, it is.
So that would be, you know, it doesn't look like there's no right answer in that one either. If you look at the units of measure, it needs to be grams per mole, right? So it really doesn't matter how many moles you have. That's grams per mole is an intensity factor, so it doesn't matter how much you have. That value is going to be the same whether you have 3 moles or 1,000,000 moles. And you just say 2 nitrogens is 14.01 times 2 is 28.02, and I don't see 28.02 in here anywhere, right? So there's no right answer for that one either. Okay, well, we just skip it then. If they want to be that way, then we won't play that game. The next one is going to take some doing. This is one where you go all the way from percent composition through to the end to molecular formula. Now let me see. Yep, I'll give you a hint. It says you have carbon, hydrogen, and oxygen in vitamin C, but it only gives you values for carbon and hydrogen. So how do you find the oxygen? Well, it says that there are only these 3 elements in there. If it gives you 2, then the other one has to be what's left over, right? So you subtract 40.9 plus 40.58 from 100 to get your oxygen. Okay, so I'll let you take it from there. And starting now. I have to use my calculator for this one. Right. Okay. The answer's there in this one. And that was 3 minutes and a quarter, so I'll give you till 6.5 minutes. So you got about another 3 minutes. 17. And I'll go ahead and put some of this up there. This one is 40.9%. And okay. So what's the verdict for 17? Let's see. All right. Any takers? How far did you get? Did you find the empirical formula?
I got E.
E?
I don't think I did that one right.
No. It's the wrong ratio. How about you, Brett? You get anything?
B.
Okay. You got the empirical formula, yes. But it asked for the molecular formula. So you need to go the next step. Okay, so here's what it looks like. 40.9%, 4.58%. So what's left over? 54.5%. Is what's left over for oxygen. And add those together, you should get 100%. So now we need to assume that we have 100 grams of sample. If we do that, then this becomes 40.9 grams of carbon, 4.58 grams of hydrogen, 54.5 grams of oxygen. Then we want to convert to moles so we can get the molar ratio of the elements in the compound. So that's grams, grams, grams. Notice I've got an assembly line going here. Same thing, same operation, each one. And just fill in the different numbers here. 12.01 for carbon, 1.01 for hydrogen, 16 for oxygen. Okay, so 3.405 here. Okay. And 4.535 here, and 3.406 here. Okay. So that's moles of each, mole ratio of each one. That establishes the molar ratio of each element in the compound. Now to find the empirical formula, you need a whole number. So we would just divide through by the smallest one as our first step. Okay, this one is obviously going to be 1. This one's going to be 1.33, and this one is so close to 1, it might as well be 1. So now we need to get rid of that fraction, that 0.33. So you know if you multiply 0.33 times 3, you get 1, because 0.33 is a third. A third times 3 is 1. So we multiply the whole thing through by 3. And we get 3 here, 4 here, 3 there. So that gives us the empirical formula, C3H4O3. And now we need the multiplier. What's that X that gives us the molecular formula? Well, the empirical weight for this compound, if you add them up, 3 carbons, 4 hydrogens, and 3 oxygens, you get an empirical weight of 88.07. Let me do it this way. The empirical weight is 88.07 grams per mole. But the molecular weight, or the molar mass for the compound, is given as 180 grams per mole. So what's the ratio there? Well, the ratio is approximately 2, very close to the whole number 2. So that means if this is 2, C6H8O6 is the molecular formula. Now this is ascorbic acid, vitamin C. We should use that in the lab all the time for analytical purposes. It's a very good antioxidant, right? It scavenges free electrons and free radicals. That's why it's good for your body, because in the metabolic processes in your body, they tend to produce free radicals. That is, molecules that have an unpaired electron, and they're extremely reactive. And that's not good for things like DNA and even proteins. Those free radicals will wreak havoc in your system. So that's why a substantial amount of vitamin C or ascorbic acid in your diet is good for your general health. It scavenges those bad molecules out of the way. But it's C6H8O6. All right, 17's done. So now we need to go to 18. All right. So this one takes a little, I don't know, maybe I'll just show you this one. I don't know, I'll give you a chance. All right, I'll give you a chance to do this one. Okay. I shouldn't rob you of that opportunity. So I'll start the timer now while I'm erasing and give you a head start. So now I'll jump on the horse. Compound. Let's see. Okay, 2.5 minutes. I'll give you till 5, and see if anybody's reasoned this one out. Let's see. I'll take a bathroom break while I'm waiting. I'm in class now. Okay. Let's see what we got here. Any takers? Nope. Okay. This one can be can cause you to pull your hair out if you have any. Okay, so let me work this one out for you. So we got a compound that's X2Y, and that could be anything, right? It's just hypothetical. We know that's the ratio of element X to element Y. And we're also given that in this compound, X represents 60% of the mass of the compound. So X is 60%, okay? That means Y is 40%, correct? So if you have 100 grams of this compound, how many grams would be each one? Okay. So this one would be 60 grams of X and 40 grams of Y. Okay, so far so good. Well, if Y is 40 grams for 1 unit, then how many is X for 1 unit? 1 unit of X is 30 grams per X and 40 grams per Y. Okay, so if you have one, that's the ratio. Mass, mass. Now it says take X2, Y2. And now it wants to know what's the percent of Y by mass. So now that we have these ratios here, 30 grams per X would be what? 30 times 2 would be 60 grams, correct? And 2 Ys would be 40 times 2 would be 80 grams, right? So now what's the percentage? The question is for Y, so we just have to do Y percent. So it would be 80 divided by 80 plus 60 times 100. Right? So 80 divided by 140 times 100 gives us the exact number is actually 57% Y in that compound. Okay? So you pick the best answer because 57 is not one of the choices. In this case, I would pick E, 60%. Okay? I know that stretches your credulity, I guess you would say. But before we understood, back in the end of the 19th century, before we understood that the ratios in atoms, the ratio of atoms in a molecule establish and lead to the ratios of mass. They only understood before that there was a mass ratio, right? And for each compound, the mass ratio was always the same, right? Definite proportions, the law of. So they would have been quite familiar and comfortable doing this type of calculation. But now that we understand that it's actually the atom ratio in the molecule that determines the that leads to the mass ratio, then we sort of lost touch with that mass-mass ratio arrangement, the ratios. And this type of problem is meant to bring you back down to our foundation, because mass came before molecules and atoms. All right, 2 more to go. And we're doing good on time. Oh, this is a simple one. All right, you should be able to do this one almost as fast as I can. Number 19. Start the timer now. Okay. Yes. 2, 2, 1, 3. See if I did that right. Right. Okay, that was 40 seconds. I'll give you a minute and a half. Oops, that's not right. Or is it? Yeah, that's right. Okay. I ought to have some takers on this one. So what is the molar mass of H2CO? Nobody? Is anybody still there?
Yeah, I'm still here.
Okay. You got it?
I've been paying attention. It's just this subject is like.
I'm sorry?
I said I've been paying attention. It's just like this subject is a little harder for me, so I've been watching you solve it.
How about you, Brett? No? All right. Well, you need 2 hydrogens. You need 1 carbon. And you need 1 oxygen. .03 grams per mole, which is E. By the way, that is a real molecule. In fact, if you've ever worked in a or had a class in an anatomy lab of any kind, you will have smelled that molecule. That is formaldehyde. And it looks like this. Right? 2 hydrogens here, off of that carbon, and 1 oxygen with a double bond. That's formaldehyde. It's the simplest aldehyde of all the groups. Anything that's got that group right there is called a carbonyl, with a carbon and a double up bond oxygen and a hydrogen off the very end of the molecule is an aldehyde. And then you can have more carbons over here, and they're all aldehydes, but that's the simplest one. Okay, so that's 19. Now we just do 20 and we're done. Okay, start the timer now. And let's see. Let's work it out. So we got this one, acetylene gas. Okay. Carbon. And okay. 2 minutes, I'll give you 4 minutes. 2 more minutes. And let's see, I'll write what we know up here now. 92.3% carbon. Hydrogen, 7.7. And we also know the molecular weight. Yep, okay. That's given information. Another minute. You have 30 seconds. All right. How about number 20? What is the molecular formula for acetylene? No takers?
A.
No. That's methane. And Brett's already left us. So I guess I'll work the problem. Acetylene. Every welder knows acetylene, like oxyacetylene torch they use for cutting. So that particular brand of torch produces a very high temperature at the tip of that, tip of the wand. But we want to know what's the molecular formula, and we're given this information: 92.3% carbon, 7.7% hydrogen, and then the actual molecular weight is 26 grams per mole. Okay, so if we assume that we have 100 grams, then that makes this and this both grams. Now we can convert to moles and find out what the molar ratio of carbon to hydrogen is. Those are the only two elements in this compound. Okay, and for hydrogen, all right, so what do we get? 7.69 and 7.62. Now we could go to the trouble of dividing through by the smallest one, but if you just look at it, they're almost exactly the same, which means they're approximately 1-to-1 ratio. So 1-to-1 ratio written out in a formula would be CH, just one of each. So what is the empirical weight of this one? Well, if we add carbon to hydrogen, we get 13.02. So that's the empirical weight is equal to 13.02 divided into the molecular weight, and you're approximately 2. So our X is equal to 2. And that means our formula is C2H2. Okay? D. D is the answer. All right, so that's our practice class for today. We'll pick it up. What, we meet again on Thursday, don't we? Thursday, and I'll just go through a complete review of the chapter on Thursday. And be sure and work those sample problems in the review document and come back with issues. I think we've established some issues today that need to be worked on. And the review document may reveal some others. So once we get to that point, I prefer when we start the class for you to bring up issues that are where you're falling short, and we'll work them out. But if not, then I'll just jump into the review. Okay. So we're finished a little bit early, 15 minutes. Actually, 8 minutes. So I'll see you again on Thursday. Let me stop the share.